Hi everyone. Today we're going to be beginning topic 4, which is on systems of linear equations. In this topic, we'll discover 3 different ways to solve systems of linear equations. The first is solving a system by graphing, the second is solving by substitution, and the third is solving by elimination or linear combination. We'll begin with section 4.1, which is solving by graphing. These begin on page 2. So I want to start first by taking a look at this graph here. This graph shows the new coronavirus cases each week per 1 million residents, and this graph is from 2020. Question 1. Where were the lowest number of new cases on June 1st in 2020? So looking at the x-axis, I can find June 1st here, and the lowest number is this blue line, which corresponds to Europe. So the answer to number 1 is in Europe. On number 2, on approximately what date did Canada and Mexico have the same number of new cases? So Canada is this purple line, and Mexico is this green line. They have about the same cases right around here, which is approximately around June 1st. For number 3, find the patterns for Brazil and the US to answer these questions. 3A. In what month did Brazil and the US have the same number of new cases? Taking a look at the graph, we have Brazil as this yellow line and the US as this red line. I see that they have the same number of cases right around here, which is between the dates 5-1 and 6-1. So that tells me that they must have had the same cases during the month of May. 3B, how many new cases were there in Brazil and the US at that time? So looking at where they have the same number of cases, over on the y-axis, we can see about how many cases were they. All the way over here, we've got around about 500 cases, or maybe just under 500. Number 4, on the graph, how did you determine when the two locations had the same number of new cases? We determined this by looking at where the graphs of the lines crossed, or where they intersect. So where the lines intersect. Okay. On the following page, we're going to go ahead and work on this activity together on the TI Inspire. If you're working on this with me in class, I've distributed this program out to each of you. But if you're following along at home, you can just follow along with the video. The program is called Solving Systems by Graphing. So this is what it looks like. On page 1.1, it says read page 1.1 and fill in the blank. The goal is to explore the blank to a system of linear equations. In this activity, the goal is to explore the solution to a system of linear equations graphically. So we are exploring the solution. On page 1.2, we can hit the control and the right arrow to move from pages 1.1 to 1.2. We can go backward by clicking control and left arrow. So let's head over to page 1.2. Control and right. So here we see these two lines here. We've got this red line, f1 of x, and we've got this green line, f2 of x. We're looking for the equations of those lines. So the red line has equation f1 of x equals x plus 1. And the green line has equation f2 of x equals negative x plus 3. Now here, it says to grab the point that you see on the x-axis. So on the x-axis, you can hover over the point that you see, hover your open hand over the point, and press Control and then click on the center button to close the hand and grab the point. You'll see the hand go from open to closed. To let go of the point, you can just click the center button again. So let's go ahead and do that. So here is the point. I'm going to close my hand over it. I'm going to hit Control and then grab the point. And I'm going to drag it around. And as you can see, it is also labeling points along each of these lines. Okay. So in part C, move the point to the left or right as needed to answer the questions. So let's move the point over to x equals -2, and we'll write the ordered pairs for each of those lines. So back to the Inspire. I'm going to grab the hand and move it to x equals -2. On the red line, we have the coordinates -2, -1. And on the green line, we have the coordinates -2, 5. Now let's move the point to x equals 4. And let's find the coordinates on each of the lines again. So grabbing that point again, that's Control and Enter. I'm going to go all the way to x equals 4. On the red line, I have the ordered pair 4, 5. And on the green line, I have the ordered pair 4, -1. Okay. Number 3, now move the point until you find a location where the coordinates are the same for both lines. What was the ordered pair? What ordered pair was the same on both lines? So let's see. I can see that the ordered pair is the same right about here at 1, 2. And something special is going on at this point. Are there any other points that are the same on both lines? Why or why not? If we were to take a look at this graph, I don't see any other points that these have in common. I can drag this all I want from left to right or right to left, and none of these points are the same except for the single point 1, 2. So think about that for a minute. Why do you think that is? The reason why is because that is the only point that they have in common, because that's where the lines intersect. So are there any other points? No. The only point that is the same is where the lines intersect. Okay. When we work with two or more lines at the same time, this is called a system of linear equations. So a system is just multiple linear equations. The point that is located on both lines is called the intersection point. The point that's located on both lines is known as the solution to the system. And the solution to the system, shown on the Inspire for this activity, is the ordered pair 1, 2. And the last question, is the point 4, 5 that we found in 2b a solution? Why or why not? So back to 2b, 4, 5 was on the red line. But on the green line, it was 4, -1. So no, this is not a solution because it's not on both lines. So no, it is not a solution because this point is only located on the red line and not the green line. All right. So that's it for the Inspire activity. Let's continue on. A system of linear equations consists of two or more linear equations containing the same variables. So in most cases, we're going to be using x and y, though you may see some other variables. The graph in the warm-up represents a system of equations. So that coronavirus cases graph is a system of equations, not necessarily linear though. To solve a system means to find the intersection point of the lines. The solution, or the point of intersection, is the point that the lines have in common. So where those lines intersect is the solution, and it's a point that both lines have in common. The point of intersection is the solution because the coordinates satisfy both equations. So if we were to plug in the xy coordinates into the xy equation, then both of those equations would be true for that ordered pair, that set of points. All right. So now let's find the solution to each of these systems of equations. Remember, it's where the lines intersect. So for number 1, I see that the lines cross or intersect right here, which has coordinates 3, -1. For number 2, they cross right here, which I know have coordinates -2, +1. Number 3, these lines do not intersect. They're parallel lines. They do not intersect, and therefore there is no solution. Which makes sense if the solution is where the lines cross. Number 4, now we're given the solution and we should come up with a graph of the equations. So we know that the solution is at 2, 4, which is right about here. So all we need to do is just graph two unique lines that cross through this point and only this point. So I'm going to draw in a line right here and maybe a line like right here. Don't forget those arrowheads because both of these lines extend infinitely in both directions. So your graph may look a little bit different than mine. As long as they cross at the ordered pair at the coordinate 2, 4, then you've got a valid solution. All right. So let's consider the number of solutions, what the graphs look like, and what the slopes and y-intercepts would be. So in the first example, we have one solution. They intersect exactly once. Notice that the slope of these two lines are different. One is positive and one is negative. If you have two lines with different slopes, you could have the same y-intercept or you could have different y-intercepts. It doesn't matter. You're still going to have one solution. So it doesn't matter if it's the same or different. It can be either same or different y-intercepts. For no solutions, we have parallel lines. They never intersect. These have the same slope, but different y-intercepts. So as we can see here, the steepness of each of these lines is the same, but the y-intercept is different. This one is at 1 and this one is at 3. And last, we have infinitely many solutions when we have the same slope and the same y-intercept. So if we have the same slope and same y-intercept, we have exactly the same line. So you can't really tell on this graph here, but both of these lines are stacked right on top of one another. We have two coincident lines. All right. Let's go ahead and flip the page. Number 5, find the slope and y-intercept of each line in the system and determine the number of solutions. So in the top equation, I see we have this in standard form. I'm going to go ahead and put this into slope-intercept form, y equals mx plus b. So rewriting the equation, 4x plus 2y is equal to 12. I want to solve for y. So I'm going to subtract 4x from both sides, and I get 2y is equal to negative 4x plus 12. We have a negative 4x and a positive 12. To get y by itself, I'm going to divide both sides by 2. And be careful here, we want to divide the entire right-hand side by 2. So that tells me negative 4 divided by 2 is negative 2x. And then 12 divided by 2 is positive 6. So this top equation can be rewritten in slope-intercept form as y equals negative 2x plus 6. Therefore, the slope is the number in front of x, which is negative 2, and the y-intercept, as an ordered pair, is 0, 6. For the bottom equation, this is already in slope-intercept form. So the number in front of x is our slope, which is negative 2. And the number, the constant tacked on at the end, is positive 10. So our y-intercept as an ordered pair is 0, 10. We're not going to graph them, but if we did, would they be intersecting parallel or the same line? Well, they have the same slope, both negative 2, but different y-intercepts. So that tells us that these lines would be parallel, meaning parallel lines, meaning they have the same slope but different y-intercepts. So how many solutions would this system have? Well, we know that parallel lines have 0 solutions. Okay. To solve a system of linear equations by graphing, we're first going to graph each equation in the system on the same grid. So using any method, depending on the form that it's in, it could be in slope-intercept form, point-slope form, or standard form, or none of them. We can graph any of those lines. Okay. Step 2 is to find the point of intersection, which is the solution. And finally, we write the solution as an xy ordered pair, and we check the solution by plugging in those coordinates into both equations for x and for y, and see if those equations are true for both of the equations. A quick note, in order to solve a system of linear equations by graphing by hand, you must use a straight edge and draw the line as accurately as possible, or the point of intersection might be incorrect. So if you're following along with me on paper or on Kami, please make sure that you're using a straight edge or the straight line tool on Kami to graph the line as accurately as possible. Another note that I have is to include as many points as you can in your line, and we'll see how that helps us in this example. So for number 6, here we have two lines, y equals negative x plus 5 and y equals 2x minus 4. We'll start with the slope for the top equation. The slope is the number in front of x, which is negative 1. I like to write my slopes as fractions, so this is negative 1 over 1. My y-intercept, b, is the number, the constant tacked on at the end, which is 5. This has coordinates 0, 5. So let's go ahead and graph that line. We start by plotting the y-intercept, 0, 5, and then we use our slope of negative 1 to find other points. So from our y-intercept, we'll go down 1, right 1, down 1, right 1. And I'm just going to keep going, and I want to fill the whole grid. The more points you do, the more accurate your graph is going to be. So I'm going to go all the way to the edge of the grid. Now, using your straight edge, you're going to sketch the line and draw it all the way across, cover the whole grid, and then don't forget those arrowheads. This line extends infinitely in both directions. For the bottom equation, we have y equals 2x minus 4. The slope here is the number in front of x, or not negative 2, positive 2, which can be rewritten as the fraction 2 over 1. The y-intercept is equal to negative 4. That's the constant term tacked on at the end. So we start by plotting our y-intercept, negative 4, 0, negative 4. And we use our slope, 2 over 1, to plot more points. So here we'll go up 2 and to the right 1, up 2, right 1, up 2, right 1. And again, plot as many points as you can. So I'm going to go ahead and sketch this graph here. Use your straight edge. And hopefully your drawing is a little bit better than mine. I'm doing this free-handed. Hopefully you're using a straight edge, and you can see pretty clearly what the solution is. So here I notice that the one point that they have in common, the place where they intersect, is right here, which has coordinates 3, 2. So the solution to my system of equations is 3, 2. Let's go ahead and check the solution by plugging it into both of the equations. So I'll start with the top equation. Y equals negative x plus 5. And I'm going to plug in 3 for x and 2 for y in this equation. So we have the equation 2 equals negative 3 plus 5. And I'm going to plug these in using parentheses. In this case, it doesn't matter a whole lot, but it's good practice to be plugging. Anytime you substitute anything into equations, you're going to be using parentheses. Sometimes we'll see in the next section when we solve by substitution, we'll see how important that is to substitute using parentheses. So now simplifying or evaluating the right-hand side of this equation, we have negative 3 plus 5. And we know that negative 3 plus 5 is positive 2. So this checks out. We have to check the other equation, y equals 2x minus 4. So I'm going to plug in 2 for y, and I'm going to plug in 3 for x. So here we have 2 is equal to, well, 2 times 3 is 6, minus 4. And evaluating the right-hand side, we know that 6 minus 4 is indeed equal to 2. This is a true equation. So it checks out in both of those equations. So we know that our solution is correct. All right, let's move on. Number 7. So to graph this line, I'm going to start by rewriting the first equation in slope-intercept form. So we have 2x minus y is equal to 8. I'm going to solve for y. So subtracting 2x from both sides, I get negative y is equal to negative 2x plus 8. And last, I'm going to get rid of that negative out in front, so divide both sides by negative 1, and I get y equals positive 2x minus 8. So that tells me that my slope is equal to 2, or 2 over 1. And my y-intercept is equal to negative 8, which has the coordinates 0, negative 8. We'll go ahead and plot that point, and then use our slope, 2 over 1, to plot other points on the grid. So go ahead and plot as many as you can. And draw your line. Ooh, I could use a straight edge. All right, so there's our line. For the other equation, we have x equals 3. We know that whenever we have x equals a number, this tells us that we have a vertical line. So we're going to go ahead and plot x equals 3. And your y value can be anything. So it could be 2, it could be 5, it could be 10, it could be negative 7. Any of these y values are fine because the equation doesn't tell us anything about y. All of our x values are going to be 3 because our equation is x equals 3. So we're going to go ahead and draw on that vertical line at x equals 3. And I see that the solution is right here at positive 3, negative 2. We're going to go ahead and check our solution by plugging it into both equations. So the very first equation, we have 2x minus y equals 8. I'm going to plug in 3 for x and negative 2 in for y and see if that is equal to 8. So evaluating the left-hand side, 2 times 3 is 6. Minus negative 2 is the same as adding positive 2. So we have 6 plus 2. Is that equal to 8? It sure is. So that checks out. In the equation x equals 3, we're just plugging in 3 in for x because there is no y. And indeed, 3 is equal to 3. So that checks out as well. All right, let's try number 8. Here we have y equals 3x minus 5 and 3x minus y equals negative 2. So here the first equation has a slope of positive 3, or 3 over 1, and a y-intercept of negative 5. We'll go ahead and plot that point, 0, negative 5. And using our slope, we're going to plot more points. So up 3 and right 1. Extend that all the way to the top of the grid. So now we're going to draw in our line as best we can. Use that straight edge. And we've got this here. For the other line, I want to put it in slope-intercept form. So solving for y, I'm going to subtract 3x from both sides. I get negative y is equal to negative 3x minus 2. Dividing both sides by negative 1 gets y by itself, so we have positive 3x plus 2. This tells us that our slope is 3, or 3 over 1, and our y-intercept is 2. So we can plot the ordered pair 0, 2, and we have a slope of 3. So again, go ahead and fill that grid. You can also go to the left 1 and down 3. So we're going to go ahead and fill the grid. Okay. And notice what's going on here with our graph. These lines do not cross. They are parallel. So our solution is, well, there is no solution. And we can check this because these two equations of these lines have the same slope, but different y-intercepts. Okay. All right, number 9. So here we have 2y equals negative x plus 4 and negative x minus 2y equals negative 4. I'm going to start by putting this top equation into slope-intercept form. So that means dividing both sides by 2. We have y equals, well, negative x divided by 2 is negative 1/2 x, or negative x over 2. And 4 divided by 2 is 2. So this tells us we have a slope of -1/2 and a y-intercept of 2. For the other line, let's go ahead and put that in a slope-intercept form. First, we're going to add x to both sides, and we get -2y is equal to x minus 4. Dividing both sides by -2, we get y is equal to -1/2 x plus 2. So this has a slope of -1/2 and a y-intercept of 2. So let's go ahead and graph the first line. Here we have a y-intercept of 2, so ordered pair coordinates of 0, 2. And our slope is -1/2, so we go down 1 and right 2. I'm going to go ahead and plot as many points as I can. You could also go up 1 and left 2 to get more points on the other side of the y-intercept. So let's go ahead and do that. Draw out your line and don't forget your arrowheads. To graph the other line, here we have a y-intercept of 2, so that's also at 0, 2, and a slope of -1/2. So we can plot those points again. So this line, you might have noticed, if you're using a straight edge, it might be hard to tell these two lines apart. But as you can see, we've got these two lines sitting right on top of one another. Graphically, this is what it looks like when you have the same line. So because these two lines share all of their points, and there are infinitely many points on a line, there are infinitely many solutions to this system of linear equations. And we can check this because they have the same slope and the same y-intercept. All right. Let's move over to the next page. So now we're going to do some modeling with systems of linear equations. Example 1, 2 of the HP deans came up with a detention buyout to raise money for charity drive. Students can pay money instead of serving their detentions. Mr. Rome is offering $9 to start plus 50 cents per detention. Ms. Lopez is offering $2 per detention. Let's write an equation for both of them that represents the total cost y in terms of the number of detentions assigned, or x, for each dean. So Mr. Rome's equation would be the total cost y is equal to the starting cost, which is $9, plus 50 cents per detention. So 50.50 times each detention x. Ms. Lopez is just charging a flat rate for each detention, so the total cost would be y equal to $2 per detention, or times the number of detentions. So here we have these two linear equations. Part B asks us to graph both of these equations on the axes, on the grid below. So the first one was 9 plus 0.5x. So this has a y-intercept of 9. And we know that the slope 0.5 can be rewritten as a fraction 1/2. So I'm going to go up 1 and to the right 2. And so we can extend this line all the way out. I'm going to just plot every single point that I can on this grid, and that way I can get a really accurate graph. If you're using a straight edge, then you can go ahead and draw just a few and then use your straight edge to plot the rest of them. All right. So this is the line for Mr. Rome. So I'll go ahead and label that too, Mr. Rome. For Miss Lopez's equation, we have y equals 2x. So the y-intercept, the constant tacked on at the end, well, there's nothing that we are adding or subtracting to our x term, so our y-intercept is 0. However, our slope is 2. In other words, 2 over 1. So we can go ahead and plot those points. And again, I'm going to plot as many as I can on this grid, just so that I have a really accurate line. Okay. So go ahead and connect your dots, draw your line, use that straight edge. Remember, the accuracy of your line is going to help find the solution to the system. And I actually almost forgot, we want to label our axes. So our y-axis, what does y represent? Y represents the total cost. And what does X represent? X represents the number of detentions. Okay. Part C, when is it cheaper to buy out from Miss Lopez? So looking at this graph, we can see that Miss Lopez is this steeper line. So it's cheaper, the total cost is cheaper between 0 and about 6 detentions. So anything less than 6 detentions or 0 to 5 detentions. Part D, what does the point 612 represent in the context of this question? Well, 612 is where these lines intersect. So that's where the cost, the total cost, is equal for each of them. And it also happens to be equal number of detentions for both of them. So that tells us that the cost of 6 detentions, and that's for either dean, is $12. Okay, part E, the third dean, Mr. McCord, is offering a flat rate of $18 where you pay up front for all detentions during charity drive. Determine the equation of this line and add it to the previous graph. So Mr. McCord is just offering $18, just a one-time flat fee of $18. So this is the horizontal line, y equals 18, where the total cost is just $18. So let's go ahead and graph that line. So this is a horizontal line at y equals 18. So that's Mr. McCord. Part F, when does it cost the same amount of money for you to buy out from Mr. Rome or Mr. McCord? So now we want to find where Mr. Rome's line and Mr. McCord's line intersect. So I can see that it's right about here at x equals 18, or at 18 detentions. So when does it cost? At 18 detentions. All right, let's try another example. Example 2, the total cost for the Math Team t-shirts at Team Tops is made up of a setup fee and a charge for each t-shirt as represented by the graph. Super Shirts has a no setup fee but charges twice as much for each t-shirt as Team Tops. Watch the scale on the y-axis. So part A, what is the setup fee for Team Tops? So this is saying what's that flat rate you got to pay right at the beginning. Well, Team Tops is this blue line here. So right at the beginning, you have to pay our y-intercept, $75. What is the charge per shirt? So as you increase the number of shirts, how does the price change? Well, we have to find the slope of this line. So I can see a couple points here. I see we've got 0.75 and we've got like 5, 100. We could also plot like 10, 125. That's another good point. But let's go ahead and use the point 0.75 and the point 5, 100. So to find the slope, we're going to use our slope formula, m equals y2 minus y1 over x2 minus x1. So our y2 is going to be 100, our y1 is 75, our x2 is 5, and our x1 is 0. So evaluating this, we get 25 over 5, which is just 5. So this tells us that the cost per shirt is $5. $5 per shirt. Okay. Part C, write an equation that represents the cost at super shirts, then graph that line on the grid provided. So let's go back and see. Super Shirts has a no setup fee, but charges twice as much for each t-shirt. So if Team Tops is charging $5, that means that Super Shirts is charging $10 per shirt. So that tells us if I were to write an equation, we would have the total cost is equal to $10 times the number of shirts. If I wanted a couple points here, I could construct a table of values. So plug in 0 for X, we get 0 for Y. If you don't buy any shirts, you're not paying anything. If you buy 5 shirts, then you're paying $50, $10 per shirt. And if you buy 10 shirts, you're paying $100. So let's go ahead and graph that. So we have 0, 0. We have 5, 50. We have 10, 100. 15, 150, and so on. So go ahead and use your straight edge, connect those dots, and draw that line. All right. Part D, which of the following statements is always true? It is true. Number 1, it is always cheaper to order from Super Shirts. Well, that's not always true. After a certain number of shirts, Team Tops actually becomes cheaper. That number is less. So it can't be 1. Number 2, it is cheaper to order 10 shirts from Team Tops than it is from Super Shirt. Let's take a look at 10. Well, it looks like right here our red line is less than the blue line. So it looks like Super Shirts is less than Team Tops. So that's not true either. It is the same price to order 150 t-shirts from either company. And that appears to be, this is the total cost. So the number of t-shirts, 150 shirts is way out there. Team Tops is going to be a lot less than Super Shirts. The price, though, where it's the same, is $150. And number 4, it is more expensive to order 20 t-shirts from Super Shirts than from Team Tops. So let's take a look at 20. It looks like, yes, it is more expensive to order from Super Shirts than it is for Team Tops. So that is true. So our answer is number 4. All right, letter E. The solution to this system of equations is 15, 150. And that tells me that for 15 shirts, the cost, and this is at either shop, is $150. All right. So now let's take a look at solving systems of equations by graphing on the Inspire calculator. So the Inspire is really nice for checking your answers, but you're still expected to show all of your work on your homework, your assignments, your test quizzes. That's where we're seeing that you know how to do this. So let's go ahead over to the Inspire and open up a new document and add a graphs page. So as soon as you open up the Inspire, you'll see this page here. Let's go back. I'm going to hit New Document. If you have an old one, you can choose to save it or not. And then we're going to hit Add Graphs. So now we can see this graph here. We're going to go ahead and write this function using function notation, f of x equals x plus 1. So in the function field, I'm going to go ahead and hit x plus 1 and then hit enter. And it's going to graph that line for me. So we can see the picture of that here. If I wanted to graph another line, then I'm going to hit tab to get back to my functions. So here I'm on the graph. I'm going to hit tab to go back to my functions, and now see I'm automatically in F2 of x. So let's go ahead and input the equation 4x minus 2, and then we'll hit enter. So 4x minus 2, and we'll hit enter, and we can see that other graph stacked right on top of the other graph. So we've got this red and blue line. Your graph should look like this. You can move the equation that appears on the screen by grabbing it with your cursor and moving it. And remember, to grab things, you can hover your open hand over it and hit Control and the center button to grab it, and then you can move it around if it's in the way. If you want a grid on your screen, you can hit Menu, View, and Show Grid. So let's go ahead and do that. So I hit Menu. View is number 2, so I'm going to hit number 2. And then Show Grid would be number 6. Yeah, let's do a line grid. We'll do that. And now we can see the grid here. To find the solutions, we need to analyze the graph. Use the Analyze Graph feature in the Inspire. So with equations graphed, we're going to hit Menu, Analyze Graph, and Intersection. So let's go ahead and do that. So Menu, Analyze Graph is number 6. And we want to find the intersection, number 4. And so now we've got this dotted line here. The Inspire is going to ask for a lower bound and an upper bound. Essentially, we want to find x values that include the intersection point in between. So I want to choose something to the left of the intersection and something to the right of the intersection. So the lower bound, I'm going to choose anywhere to the left of the intersection. Right here is where it intersects. So I'm going to choose something to the left. Doesn't matter how close you are or how far you are. I'm going to choose right there. The upper bound, I'm going to choose anything to the right. So I could do it really close to the point, but I like to give myself plenty of room. So I'll do something right over here. And it's going to automatically find the intersection point for us, which is 1, 2. Okay. So the solution using the Inspire is 1, 2. So anytime that you have two equations, you can plug it into a graph in the Inspire, use the Analyze Graph intersection tool, and that's going to help you check your work. Of course, we still do need to see you graph those lines on your own. All right. All right. So this concludes our notes on solving systems by graphing. Next, we're going to practice. We're going to learn how to solve systems using the substitution method. But before we do that, we're going to get plenty of practice on solving by graphing. All right. We'll see you tomorrow in class. Have a great day, everyone. Bye.